Now we'll go with the analysis part. T of n is 0 if n equals to 1. T of n by 2 plus T of n by 2 plus n otherwise. Sort the left part of the array, sort the right part of the array. The time required to divide and merge one instance of the solution. 2t of n by 2 plus n. 2 of t of n by 2 is 2t of n by 4 plus n by 2 plus n. Then we have 2 square t of n by 2 square plus n. Then 2 square t of n by 2 square plus 2n. So we have 2 square 2t of n by 2 cube plus n by 2 square plus 2n. 2 cube t of n by 2 cube plus n plus 2n, that is equal to 2 cube t of n by 2 cube plus 3n. That continues to 2i t of n by 2 power I plus I dot n. Let 2 power I be n. Then t of 1 be 0. n t in t of n by n plus n into I. T of 1 is 0. So ni. 2 power I is n. I into 2 power I. So I log 2 to the base 2 is equal to log n to the base 2. So that's why we have log 2 to the base 2 equals to log 2 n. I equals to log n to the base 2, log 2 to the base 2. That get cancelled. Then we will have log n to the base 2. Ni is I equals to n log n to the base 2. T of n is theta of log n to the base 2. N log n to the base 2. Example for this is 83297134. There are 4 elements. Can be divided into 4 each. Then 4 is divided into 2 each. Then will be divided into single instance. Then combining 2 each in ascending order. The first element of this, if it is greater than the second instance first element, that will be considered for the combined array. In the same way, combine all the elements. According to previous algorithm, it is not stable. Sorting algorithm is said to be stable if two objects with equal keys appear in the same order in sorted output as they appear in the input unsorted array. Some sorting algorithms are stable by nature, like insertion sort, merge sort, bubble sort. Some sorting algorithms are not, like heap sort, quick sort. Any given sorting algorithm which is not stable can be modified to be stable. In general, any comparison based sorting algorithm which is not stable by nature can be modified to be stable. That is, make it stable by changing the comparison. The standard merge sort an array is not an in-place algorithm since it requires O of n additional space. It is not stable because it changes the position of the 3. Which 3? That is, first it takes the 3 which is there in the second element side and then place it before the first occurring 3. That's why it is not stable. It is not even in place because it requires an extra array to perform the merge. Quick sort, partition, exchange, sort, which divides the input elements according to their position in the array, divides them according to their value. Low greater than high, there are no elements present. Divide array into 2 parts. Elements towards left of the key are less than the key, and elements towards right should be more than the key. K is partition. A, low, high. Return the position of the key element. Left part of the array A starts from index low to k minus 1. Sort left part recursively. Right part of the array A starts from k plus 1 to high. Sort right part recursively. After sorting the position of the key element will not change. The entire array is sorted. There is no need of merging. Algorithm quicksort A, low, high. If low is less than high, return. K is partition of A, low, high. Quicksort of A, low is greater than high. If low is greater than high, you have to return. Then K is equals to partition of A, low, high. Quicksort of A, low, k minus 1. Quicksort of A, k plus 1, high. To divide the array, assume very large value is stored at the end of the array. Procedure is to partition of the array. Keep incrementing index I as long as key greater than or equal to A of I. Do I equals to I plus 1 while key greater than or equal to A of I fails. Keep decrementing index j as long as key is less than A of j equals to j minus 1. Then while key less than A of j. Condition fails if I less than j. Exactly A of I with A of j. Repeat above process as long as I less than or equal to j. Exchange j of low with A of j and final value of j gives the position of the pivot or key element. A of low, high. Partition of A, low, high. Key A of low, I low, j is high plus 1. While I less than or equal to j, do I plus 1 while key greater than or equal to A of I. Do j equals to j minus 1 while key less than A of j. If ai less than j, exchange A of I, A of j. And while exchange A, low, A of j. A, low, A of j. Exchange. It is swapping. Return j. Here first we have 5, 3, 1, 9, 8, 2, 4, 7. We have the end position 8 as well. Firstly, we will take key as I 5. Is 5 greater than 3? Yes, it is. So I will be incrementing. If 5 greater than 1, yes. Is 5 greater than 9? No. So I will be there. Then if is 5 less than 8, S. Is 5 less than 2? No. So swapping the next position, that is j will be at the j plus first position, that is 4. will be swapped with 9. Then I will be at 4 now. So I key is 5 again. But J is at 9. Is 5 less than 4? Yes, it is. Is 5 less than 8? No. Then we'll consider J. Is 5 greater than 2? Yes. Is that 2 is greater than 5? No, it is not. So we will be swapping that again. J goes from J minus minus here as well. First J will consider from the 7. First it occurring is here is 5 greater than 9? No, pause I there. Then is 5 less than 7? Yes. Then J minus minus. Is 5 less than 4? No. So swapping 4 and 9. Swap occurred. Then now it is at 9 again. Key I is at 4, J is at 9. Now we will be swapping 8 and 2. I is 2, J is that. Exchange A of low with A of J because I equals to J. A of low with A of J. That is A of low. What is A of low? It is 2. 2 comes in first position, then goes at last position, middle position. Then sorting left part again. That gives us 2, 3, 1, 4. Again pivot element as 2. Is 2 less than 3? Yes, true. Is 2 less than 1? No. Then is 2 greater than 4? No. So this will occur as is 2 less than 3? Yes, it is. But we should check where is 2. And then is 2 less than 1? No. Then J goes from is 2 is 4 greater than 2? Yes. Then is 1 greater than 2? No, it is not. So swapping I and J. It is like is 2 greater than 3? No. So I will be passed. Is 2 less than 4s? Is 2 less than 1? No. Then it goes to be swapped. 2, 1, 3, 4. Now is 2 greater than 1? No. Then J will be at 3. We can swap them again. That is I when I is equal to J, we have to swap, exchange the A of low element with A of J. Is 2 less than 3? Yes. Is 2 less than 1? No. When J comes there, we have to swap. Sort right part. That is 3, 4, I and J. Done. That is done. Next, we have this 8, 9, 7. Tree for recursive call. Low is 0, high 7, K is 4. Then low is 0, high 3, K is 1. low 0, high 0. Low is equal to high. Then low 2, high 3, k is 2. Low 3, high 3, k is 3. Low 5, high 7, k is 6. Then low 5, high 5. Low 7, high 7. That will end. Here is another example 11995566. 1 is a pivot element. Is 1 is greater than 1? Greater than or equal to 1? Yes, it is. So I plus plus I goes till 9. Then check for j. J will be at 8th position. Check whether pivot element is less than 6. Yes, true. Pivot element less than 6. Yes, true. J minus minus. Pivot element less than 5. Correct. Less than 5. J minus minus. Less than 9. J minus minus. Less than 9. J minus minus. Less than J. No, it is not. So ij swap this a of low to a of j. Swap it. Then we have again 1. Then 995566. 1 is a pivot element now. Is 1 is greater than 9? No, it is not. So I will be staying there itself. So we will be swapping these numbers. 1 as the pivot, that will be swapped here. Left side will be 1, right side will be 995566. So 9 is the pivot element. Is 9 greater than or equal to 9? Yes. 9 greater than or equal to 5? Yes. 9 greater than or equal to 5? Yes. 6? Yes. And j is j till the last element. Then it will be swapped towards the extreme right corner. 695569. Low equals to 0, high equals to 7. 567. K is 1. Low equals to 0, high equals to 0. Low is 2, high is 7, k equals to 7. Low is 2, high is 6, k equals to 5. Low is 7, high is 7. Quicksort algorithm is not stable. Quicksort algorithm is in place, just swapping the elements within the input data structure. Best case occurs if key element is present exactly at the center, dividing the array into 2 equal parts. T of n is 0 if n equals to 1. T of n by 2 plus T of n by 2 plus n. To partition n elements, 2t of n by 2 plus n, 2 into 2t of n by 2 square plus n by 2 plus n, 2 square t, n by 2 square plus 2n, 2i t of n by 2 power I plus I into n. Initial condition t of I equals to 0, t of 1 equals to 0. Let us make 2 power I equals to n, and t is n by n, n into I, ni, 2i, 2 power I equals to n. Take log on both the sides. I log 2 to the base 2, log n to the base 2, I equals to n log n, omega of n log n to the base 2. Worst case occurs at each invocation of the procedure. The current array is partitioned into 2 subarrays, with one of them being empty occurs if all elements are arranged in ascending order or descending order. 0, t of 0 is plus t of n minus 1 plus n, worst case. Otherwise is t of 0 plus t of n minus 1 plus n. N equals to 1, then 0. Otherwise it will be t of 0 plus t of n minus 1 plus n. T of 0 is 0. T of n minus 1 plus n. T of n minus 2 plus n minus 1 plus n. T of n minus n plus 1 plus 2 plus 3 plus n minus 2 n minus 1 till n. That is t of 0 plus n into n plus 1 by 2. That is n square by 2 plus n by 2. Big O of n square. Then average case for this will be an array may not be exactly partitioned into two subarrays or may not be skewed as in the worst case. Key element may be placed at arbitrary position in the array ranging from 0 to n minus 1. Time to sort the left part, that is LBUB minus LB plus 1 is, that is k minus 1, k minus 1 minus plus 1 is k. Then right part will be like n minus 1 minus k. This is an average case. K n minus 1 minus k. While arranging highest integer value is placed at end of the given array, total number of elements n plus 1. Time unit to partition the n plus 1 elements is n plus 1 time units. T of 1 equals to n plus 1 plus t of k plus t of n minus 1 minus k. N plus 1 times total number of elements. So that is equal to average cases 1 by n summation of 0 to n minus 1 n plus 1 plus t of k plus t of n minus k minus k for n greater than equals to 1. So we have this as 1 by n average case. So that's why 1 by n we will be multiplying it. So n into t of n, that is equal to summation k 0 to n minus 1 n plus 1 plus t of k plus t of n minus 1 minus k. Then n plus 1 summation n plus 1 summation 0 to n minus 1 of t of k plus t of n minus 1 minus k. N plus 1 summation of this is just n minus 1. N plus 1 into n minus 1. T of k plus t of n minus 1 minus k. T of 0, t of n minus 1, t of 1. Let us consider k as n minus 1. Then we will get t of 0 plus t of n minus 1 minus 0. Then t of 1 plus t of n minus 2 plus and so on. Replace n by n minus 1 in each iterations, so that we will get 2n plus 2t of n minus 1 and t of n equals to n minus 1t n minus 1 plus 2n plus 2t of n minus 1 divided by n into n plus 1. Replace n by n minus 1. Again we have to do the same thing for the time. Then we will get it as 2 by 3, 1 by 2, 1 by 3 and all 1 by k. 2 into 2 to n plus 1 1 by k is dk. That is will become log k. This also gives us n log n to the base 2.